going on, guys? In this video we are going to see an example of second order transient analysis, and in this particular problem we are going to see what's going to be the voltage across this capacitor when the time is equal to 0 and greater than 0. Now to find this one, what we have to do is we have to create a second order differential equation. To create that equation we can use the Kirchhoff's voltage law, and if you remember, in Kirchhoff's voltage law, voltage in should be equal to voltage out. So voltage in is 10 voltage and voltage out is going to be the addition of all the voltage across this resistor, inductor and capacitor. So we can say VR of t plus VL of t plus Vc of t is equal to voltage in, right? Now we know that voltage in is equal to 10 voltage. Now VR of t, we can replace this one with I of t times R, because we know that V is equal to IR. So this is going to be I of t times R, and VL of t, we can replace that one with L di of t divided by dt, and Vc of t, we are going to just keep it as it is, Vc of t. And again we can replace this I of t with C dVc of t over dt times R, plus L di of t over dt, we can replace this one with LC d square Vc over dt square, and Vc of t, we are going to just keep it as it is. Now if you look at this one, this is almost a second order differential equation, but this is not in standard form because we have a coefficient in front of the second order, right? We shouldn't have that one. So in order to eliminate this one, what we are going to do is we are going to divide everything by LC, and if you divide everything by LC, you're going to have this one d square Vc. I'm just writing this one in terms of order. So I write this first, like second order first. So this is going to be d square Vc over dt square. This LC is eliminated because we are dividing everything by LC. And the second one we are going to have is R over L d Vc of t over dt, and then we are going to have Vc of t over LC, that's equal to 10 over LC. So this is the final equation we get. And if you look at this second order differential equation, this is not a homogeneous differential equation because we have a forcing function after the equal sign. So this is not homogeneous. When we have a non-homogeneous differential equation, we can use the superposition technique to solve this problem. And if you remember superposition technique, that's going to be this one, addition of homogeneous plus particular solution, right? Be particular. So this is the one we are going to use. First let's find the particular. To find the particular, what we do is particular, let's write particular. To find the particular solution, we divide this forcing function by omega n square. So this is going to be 10 over LC divided by omega n square, right? We have to find out the omega n value, and also to find the general solution, not general solution, homogeneous, because addition of homogeneous and particular solution is going to be the general solution for this non-homogeneous differential equation. Now to find the homogeneous, we have to know what system this one is, right? There are three different systems. We can have overdamped response system, we can have underdamped response system, or we can have critical damped response system. To determine that one, we have to find the zeta value. To find the zeta value, we use this equation 2 zeta omega n is equal to R over L. First we have to know what's the omega n value is. To find the omega n value, we use this equation, that's omega n is equal to square root of 1 over LC. We know the inductance and the capacitance, that's here. Our inductance is 2 henries, capacitance is 0.5 microhenries. So this is going to be 1 over inductance, that is 2, capacitance is 0.5, so this one multiplication 0.5 micro is going to be 10 to the power minus 6, and this is going to be 10 to the power of 6 divided by 1, because 2 times 0.5, that's going to be 1 in the square root, so this is going to be just 10 to the power of 3, right? So that means 1000 radians per second. So this is our omega n value. Now we can use this omega n value to find out the zeta value. So 2 times zeta times omega n, that's going to be 1000. That's equal to resistance over the inductance. Resistance is 1 kilo ohm. Kilo ohm in 1000, so this is going to be 1000 divided by the inductance, that's going to be 2. From this one we can see these two are going to cancel each other, and we are going to have, okay, there's something wrong. 2 zeta inductance is 2. 2 zeta times, let's see what's the mistake. 1000, oh, this one should be multiplication, right? 2 zeta omega n r over L. Okay, let's rewrite this one. Here we go. And if we rearrange this equation, this is going to become zeta is equal to 1 over 2 omega n times r over L. So 1 over 2 times omega n is 1000. So 2 times 1000 times the resistance, that is 1000, divided by 2. Okay, now we can see these two cancels each other. 1000 cancels each other, we get 1 over 4. 1 over 4 is equal to 0.25. So when we have the zeta value that is less than 1, right, if it's less than 1, this is an underdamped system. This is underdamped system. Okay, so the general solution for this this homogeneous differential equation is going to be in this pattern. That's going to be k1 cos omega dt. Okay, let's rewrite this one. K1 cos omega dt. Omega d should be subscript, so omega dt, and then k2 plus k2 sine omega dt all together times e power negative t times sigma. So this is the general solution for this homogeneous differential equation when we have underdamped system. Now using this one we are going to write our homogeneous answer, but we have to find out our k1 value, k2 value, and also we have to have omega d value. But before I do that, I'm going to just bring the non-homogeneous general solution. Okay, that's going to be just the addition of particular solution and the homogeneous solution, right? Okay, let's note this zeta value and this omega n value here and get rid of this part. And we know that zeta value is equal to 0.25 and omega n value is 1000, right? 1000 radians per second. Radians per second. And now I am going to get rid of this part. Get rid of this part. And let's continue here. Here we have the particular solution. We created the equation, but we didn't find the final answer, right? So instead of writing like this, we can also write this one as 10 over LC omega n square. And we found out the omega n value, that is 1000. So this is going to be 10 over inductance is provided, that is 2 henries. 2 times the capacitance is 0.5 microhenries. So this is going to be 0.5 times 10 to the power minus 6. And then we are going to multiply this one with omega n square, and if you square 1000, that's going to be 10 to the power of 3 square, that's going to be 10 to the power of 6. From this one you can see this 10 to the power of 6, 10 to the power of 6 going to cancel each other, and this 2 times 0.5, that's going to be just 1, and if you divide 10 by 1, that's going to be still 10, right? So this is our particular solution, and this is our homogeneous solution, right? We see homogeneous, we found out here, because when we have underdamped system, this is going to be the pattern. That's how we derive this one. Now to find the non-homogeneous, we see non-homogeneous general solution is going to be addition of these two, 10 plus this one. So this is going to be 10 plus k1 cos omega dt plus k2 sine omega dt times e power negative t sigma. Now we have to find k1 omega d, k2, and also we have to find out this sigma value in order to give the particular solution for this non-homogeneous differential equation. Now in order to bring that one, we had to know the initial conditions. Now let's look at some initial conditions. We had to know what's going to be the initial voltage across the capacitance, and also we had to know what's going to be the initial current across the inductance. Now to find this one, we have to see what's going to be the voltage across the capacitor before the switch is closed, because when time is equal to 0 we are closing this switch, but just before we close this switch the voltage across this capacitor is going to be 0 because there's no current flowing through this one, right? So voltage across this capacitor is going to be 0. So when we close this one, the voltage doesn't change immediately. So what's going to happen is at Vc of 0, the voltage across the capacitor is going to be still going to be 0. So we take that one first. And also we have to know what's going to be the current through the inductor. And before we close the switch, the current through the inductor is 0 because if we open the switch, there's no current flowing through that one. So current through the inductor is 0. When we close the switch, what's going to happen is the current through the inductor doesn't change immediately. So still current through the inductor is still going to be 0, right? So these are the two initial conditions we are going to have. Now we are going to use these two conditions to find out our k1 and k2 value. Okay. Now since we have Vc condition, we can directly plug this one in this equation to find out instead of writing Vc homogeneous, I'm going to write this one as Vc of t. In that way it will be clear. Okay, when time is equal to 0, this is 0. That's the one I'm going to do first, right? So let's go ahead and do that one. Vc of 0. So when the time is equal to 0, we are going to have k1 cos omega d times 0. This time is going to be 0, right? And also here we are going to have 0. And when we have sine 0, this whole thing is going to be 0 because sine 0 is 0. This whole thing is going to be 0. So this one we can eliminate. And also when we have e power negative time is equal to 0, this is going to be, the whole thing is going to be 0. And we know that e power 0 is equal to 1. So this is going to be just 1. So we can get rid of these two parts and we can write this one alone. Right? And also I forgot to write. Okay, this is for homogeneous. This is for non-homogeneous because we had to have 10 in front. This is particular solution, right? Particular plus homogeneous is this one. So we have to use this one. So this is going to be 10 plus k1 and cos 0. When time is equal to 0, cos is going to be 0. So this is going to be just multiplication with 1. And here we know that when time is 0, sine is 0, the whole thing is going to be 0. And this one is going to be just 1 because e power 0 is going to be 1. So we can get rid of that part. From this one we can see that k1 is going to be equivalent to, because Vc of 0 also 0, we can say 0 is equal to, before we do the next thing, we can write 0 is equal to 10 plus k1. Therefore k1 is going to be equivalent to negative 10. Now we have found out the k1. Our next thing is to find out k2. To find out k2, we are going to use this I of 0 condition. Okay. And instead of writing I of 0, you can write this one as c times dVc over dt. This is another expression for I of t, right? Now that's what we are going to use because this is the derivation of this one, this equation. This is our Vc of t. This is the derivation of equation multiplied by c. And if you find the derivative of this one, but before we find the derivative, let's multiply this e power negative t sigma. In that way it will be easier. Okay, if we multiply this e power negative t sigma with this one, this is going to give us Vc of t is equal to 10 plus k1 e power negative t sigma times cos omega dt plus k2 e power negative t sigma sine omega dt. Okay, so this is the multiplication of this e power negative t sigma. Now let's go ahead and take the derivative. I'm going to take care of this part first, then we can multiply this one with c. Okay, so this is for this one. This is for the current we are looking at. Now let's take the derivative of this one. Vc prime of t is going to be equivalent to, if you take the derivative of 10, that's going to be just 0. And when we consider this part, this is going to be a product rule because we have two functions related to t, right? So let's take the derivative of this one first and keep the other one as it is. K1 is going to be a constant, so we just keep that one as it is. And if we take the derivative of this one, this is going to be multiplication of -1. Okay, so we are going to have negative in front. So let's put the negative sign in front. And then we are going to have e power negative t sigma, and also we are going to have sigma in front, because if you find the derivative of this one, t is going to be 1 and we are going to have negative sigma, and cos omega dt remains the same. Cos omega dt remains the same. Now we are going to take the derivative of cos omega dt. So when we did take the derivative of cos omega dt, that's going to be a chain rule because we had to take the outside derivative and also we had to take the inside derivative, and we keep the other one as it is. So this is going to be just k1, and this is going to be negative because of this cos, because if we take the derivative of cos, that's going to be negative sign, right? So here we are going to have negative k1 e power negative t sigma sine omega dt. Okay, now we have taken care of the first part. Now let's go for the second part. In the second part, we are going to take the derivative of this e power negative t sigma first. So this is going to be just negative sigma times k2 e power negative t sigma, and if we take the derivative, we keep the sign first as it is. So this is going to be sine omega dt. Then we keep the other one as it is, and we take the derivative sign. So this is going to be k2 e power negative t sigma, and also when we take the derivative of this one, we have to multiply this one with omega d, right? Because inside derivative is omega d. So this one multiplies by omega d. And let's look at the second one. So this is going to be k2 e power negative t sigma, and if we take the derivative of this one, the outside derivative is going to be cos omega dt, but inside derivative is going to be omega d. So we multiply this one with omega d, and this is going to be cos omega dt. Okay, now we have found out the derivative, and then we are going to plug this condition. We have I of 0 is equal to 0. So derivative of this one, c times this one, I of 0 is equal to c times this derivative, c times vc prime t. Okay, so we are going to plug 0 first, but before we apply 0, let's plug 0, because if I of 0, this is going to be vc prime of 0, and if we plug 0, we can get rid of some parts. If you plug 0, all the sign will be eliminated, because when you have sign of 0, because when time is 0, this whole thing is going to be 0. So when you have sign of 0, and if you multiply anything by 0, that thing is going to be 0. So this one will be eliminated. This part we can eliminate, and that's it. So these are the two parts we can eliminate, and let's find out the rest of the equation. So minus sigma, the first one is minus sigma times k1, and when we have time is equal to 0, e power 0, that's going to be just 1. Okay, and also cos, when we have 0, that's also going to be 1. So we are left with negative sigma k1 in the first one, and let's look at this one. this one is eliminated, this one is eliminated. We have k2 e power negative t sigma. So this is going to be k2 times, so this is 1 times 1, okay. So k2 times e power 0, that's going to be just 1. So this is going to be 1. Then we have omega d, and cos 0 is going to be 1. So we just plug 1 here. The whole thing is equal to 0, right? So 0 is equal to c times negative sigma k1 plus k2 omega d. So this is what we derived. And if you move this c to the other side, 0 divided by c, that's going to be just 0, right? So we can get rid of the c also. Now let's continue this part on top. Okay. Oh, let's get rid of these things. Okay, let's get rid of these things and continue here. Okay, let's copy down this one. So we found out 0 is equal to, and we brought this c to the other side. So in that way, c also eliminated, because 0 divided by c, that's going to be still 0. So 0 is equal to negative sigma k1 plus k2 omega d. And we found out k1 is equal to negative 10. So we can plug that one here. So this is going to be negative sigma times negative 10 plus k2 times omega d, right? Now negative sigma times negative 10, that's going to be positive 10 sigma. Positive 10 sigma plus k2 omega d. Omega d, that's equal to 0. Now we have to know what is our omega d and sigma value in order to find out the k2 value. So to find that one, what we can do is we can use this equation. Sigma is equal to zeta multiplied by omega n, and we know the zeta value, that is 0.25, times omega n is 1000, and if you multiply these two together, that's going to give you 250, right? This is our sigma value. Also we have to find out the omega d value. To find out the omega d value, we can use this equation, that is omega n times square root of 1 minus zeta square. So zeta omega n, we know that is 1000. So 1000 times 1 minus zeta square is going to be 0.25 square. And if you calculate this value, you will get 968.25. Now we can go ahead and plug it in this equation to find out k2 value. Okay, let's plug it in here. So k2, so if you rearrange this one, this is going to be k2 omega d is equal to negative 10 sigma. Therefore k2 is going to be equivalent to negative 10 sigma divided by omega d. Okay, negative 10 times sigma is going to be this value, 250 divided by omega d. We calculated omega d, that's 968.25, and if you calculate this k2 value, that's going to give you negative 2.58. Now we have the k1 value, k2 value, and also we have the omega d value. Also we have the sigma. So we can write our particular solution for this non-homogeneous differential equation. Okay, now let's get rid of this part. Let's get rid of these things. Write our final answer here. I erased the k1 part. We know that k1 is equal to negative 10. Okay, k1 is equal to negative 10. These are the information we needed, k1, and also we need omega d. This is our omega d value, and also we need our k2 value. This is our k2 value, and also we need sigma value. Sigma is equal to 250, and these are the things we need in order to write our final solution. So Vc of t, therefore we can say Vc of t is equal to 10 plus k1 is equal to negative 10. But instead of writing negative 10 here, what we can do is we can take the negative here. If I take the negative common, this is going to be just 10, and cos omega d is this one, 968.25. So this is going to be 968.25 t plus k2 value is negative 2.58, but we took negative common, right? So here we are going to have positive 2.58 sine omega dt. Again, omega d is 968.25 t multiplied by this one multiplied by e power negative t sigma, and we know the sigma value that is here 250. So this is going to be negative 250 t volts, and that's going to be the final solution for this question. That's going to be the voltage across the capacitor when the time is greater than or equal to 0. Okay, and that's how we do this kind of problems. I hope this helps. Thanks for watching.